Okay, this is start off chapter 3, section 3-1. Complex numbers. I got my calculator off to the side here. Let me hide this and start from. Let's see how this works out. Complex numbers. Complex number is in the form of a plus bi, where a and b are real numbers. The number a is said to be the real part of a plus bi, and the number b is said to be the imaginary part. Imaginary number 5 plus 7i, 5 minus 7i. Pure imaginary doesn't have any a value. The a value is 0, right? So simply 7i, 3i, negative 3i, right? Pure imaginary versus non pure, right? Complex numbers. Where did complex numbers come from? Where were they discovered? Well, it goes way back. Greek mathematician, this guy named Alexandria, is noted to first conceive these numbers way back in 1572, and as time progressed, mathematicians studied it more. We've got Euler in the 1700s, and this Frederick Karl Gauss, 1777. It's been bottom line is complex numbers have been around for years and years and years and years. Why do we need complex numbers? All right, well, how did they come to existence, so to speak? It says this: some functions have zeros that are real numbers. All right, you solve a second degree equation or whatever, or even a linear equation, you get an answer that's a real number. It's 5, 6, could be negative, could be a fraction, could be a decimal. All right, but some functions, when you solve them, the answers aren't real. The complex number system is used to find zeros of functions that are not real numbers. When looking at a graph of a function, if the graph does not cross the x-axis, then it has no x-intercepts, and thus it has no real number zeros. Remember that x-axis and even the y-axis is real numbers. It's a real number system, real number line. Here's what I'm talking about. Let's say you've got a parabola, right? This is a vertex. It crosses the x-axis. It has two roots, all right? This is what's called a double root solution. You got two answers, but they're both the same. In this case, it looks to be something like x equals 2. Here's an example of a parabola. When I graph it, it doesn't intersect the x-axis. All right, it's got two roots, but they're complex. They're imaginary numbers. All right, how would we graph an imaginary number if we were studying them in depth? We use what's called an Argand plane. All right, the horizontal x-axis is the same thing, real numbers as you see them here. You got 1, 2, 3 to your right, negative to the left, but your vertical, your y-axis is given in the terms of letter I standing for the imaginary unit. All right, positive above the x-axis and negative below the x-axis. Definitions. We start out our study by defining what I is equal to. I is said to be equal to, by definition, the square root of negative 1. Therefore, I squared is the square of negative 1 squared, which is simply negative 1. I cubed can be expressed as I squared times I, meaning I cubed translates to negative I to the fourth is nothing more than I squared squared, or negative 1 squared, which is positive 1. Now, what's interesting about this, I to the fifth is the same thing as I to the first. I to the sixth would be the same thing as I to the seventh, or I to the second. I to the fifth, I to the seventh power would be the same as I to the third. I to the eighth would be the same as I to the fourth. In other words, this letter I just takes on four values. I is the square of negative 1. I squared, negative 1. I cubed, negative I to the fourth, 1. And then it repeats itself. I to the fifth is the same as I to the sixth the same as I to the second, I to the seventh, I to the eighth, and I to the 12th goes back to being just I. All right, it only takes on these four values, and you see them in red. 1, negative I, and I. Express each of these terms in terms of I. All right, there's what's five of them? So what we do is we take this radicand, negative 7, we express it as the product of negative 1 times 7. And then we separate each of these two terms under their separate radical symbols. But by definition, we know the square root of -1 is defined as the letter I. So this translates to I radical 7, or it can be written as radical 7I. I don't particularly care for this format because sometimes you think that the I is under the radical. When the I is in front, because it's times, the R doesn't make a difference. It's fairly clear. This is not as clear as that is, but they're both the same thing. All right, square root of -16, same process. We express -16 as the product of -1 and 16. Then we separate the -1 and the 16 under their separate radical symbols. And by definition, square root of -1 is defined as the letter I. All right, I times 4. Well, probably best written as 4I. Letter C, the negative of whatever the square root of -13 is. Now, he's not looking for a decimal. He wants me to express this in terms of I. So once again, I take the radicand and I express it as the product of -1 and 13. I separate these two under their separate radicals. Square root of -1 is defined as the letter I, so it's a minus times I times the radical 13. I prefer this, even though sometimes your answer sheet may give you this. But make sure here that you know the I is not under the radical, all right? Letter D, same idea. We separate this into -1 times 64, write it under the separate radicals. This is defined as I, so it's negative I. 64 is a perfect square. Square root of 64 is 8. Negative I times 8, or negative 8I, would be the appropriate way of writing that. Once again, rewrite this as -1 times 48. Separate both these terms under their separate radicals. What's different here is that 48, even though not being a perfect square, can be expressed as 16 times 3, where 16 is a perfect square. And once again, if I separated these two under their separate radicals, the square root of 16 would be 4. This would remain under the radical. I'm probably going to rewrite that as, yeah, this would be the appropriate way, 4I radical 3. You could see it with the I in the very end, because this is multiplication. It's 4 times I times radical 3. So the order in which we write this doesn't make a bit of difference. Complex numbers obey the commutative, associative, and distributive laws. We can add and subtract them, same way we subtract and add binomials. We collect the real parts and the imaginary parts, just as we collect terms of any binomial. You treat the letter I like it'd be any other variable, an X or a Z or whatever. So adding these two, but we can't even do this in our heads. 8 plus 3, that's 11. 6I plus 2I, that's 8I. All right, he does he goes all through this and he, adding the real parts and adding the imaginary parts. But 8 and 3, 11. 6I and 2I, 8I. Here you got to realize that the minus sign affects both the signs in parenthesis. All right, the 6 becomes negative. The minus 3I, a minus times a minus will become a positive. 4 minus 6 is minus 2. 5I plus 3 more I is 8I. All right, combine like terms, just like you would combine, X's and Z's or T's. You treat the I just like any other variable. You add the real part and you add the imaginary part. When the square root of the square root of A and the square root of B, when A and B are real numbers, the square root of A and B can be written as the square root of AB. Not true, however, when A and B are not. The square root of A and the square root of B are not real numbers. If any one of these is a negative, either the A or B is negative, you just can't multiply these two. All right. You can when these guys are real, but when these guys are imaginary, they contain negative signs under the radical. You just can't multiply them. All right, so what is he asking me to do here? Multiply square root of -16 times the square root of -25. What he's telling me I can't do. I can't just write one big radical and then multiply 16 times 25 and get whatever, 16 times 25 is. Here's what he's saying I can't do. If I can turn this on. All right, square root of -16. times the square root of negative 25. 25. Well, what he's telling me here is the answer is negative 20. Now let's just see how this plays. This is what my calculator is telling me. Let's see how this plays out. All right. So yeah, I get this here. All right. So we rewrite negative square of negative 16 is the square of negative 1 times 16. Square root of minus 25 is the square root of 1 times the square root of 25. Now, both these square root of negative 1s are both i's. That's an I and that's an I. All right, so I got I times 4 times I times 5. Well, 5 times 4 is going to be 20. And then, well, I take that back. This calculator hmm, did give me the correct answer, which is interesting. When both of those guys are negative, that is so weird how it gave me. The calculator was smart enough to deal with the i's. Hey, I take that back. I take that back. All right. Here's what would have yeah, the calculator is smart but did it. What he was telling me is if I take the square root of negative, if I take negative 16 and I times minus 25, minus 16 times minus 25, I'm getting 400. When you take the square root of 400 manually, you don't get minus 20, you get positive 20. So the calculator is smart enough that what it did, it took this and it broke it up just like you would do with pencil and paper. And what he's saying is if you were sitting at home and you saw this example and you went square root of this times the square root of that is the square root of their product, you'd end up with the square root of 400, which would have been a positive 20, when in actuality the answer is a negative 20. All right, Mr. Calculator is smarter than I thought he was. So he's saying that we can't do it pencil and paper, but obviously a TI handled it no problem. Um, all right, he's asking me to FOIL this out. Product of the first term is middle term 3i and 2i. Combining like terms, well, why is this minus 6? Well, by definition, I squared is negative 1. I is the square root of negative 1. I squared is negative 1. A positive 6 times what is a negative 1 gives me a negative 6. Combining these, a 1 and a negative 6 is a negative 5. All right, so let's see if my calculator can do this. I'm willing to bet it can because I just gave it major props. 1 plus 2, all right. Now, just before I even do, let me clear this off. Let me go to my mode here. I've got two decimal places. All right, I'm going to set this at 0. I wouldn't do this any other time. I would keep it around 2 or 3 places, but for this work, I'm going to set it at 0. So in parentheses, what have I got here? 1 plus 2i. 1 plus 2. Now, where do I find I? It's the second function of the period key. Second function, period, is my I. Close parenthesis, open parenthesis. 1 plus 3i. 1 plus 3, second function, the period key, closes up. Hit enter. I like it. Yeah, negative 5 plus 5i, calculator's right on. It also says here, show calculator, set A plus BI first. All right. I did the mode, but here's what I'm telling you. If you go back to mode here, all right, you come down to the next to last, you see where I got mine set. Let me set it like this. I want to set it at A plus BI. Yeah, I should have said that first. I had the note here, but I didn't say it. All right, you need to set your calculator so it understands working with I. And that's why I gave me the correct answer before. but I thought it wasn't. All right, let me clear that. 3 minus 7i squared. So open parenthesis, 3 subtract 7, second function of a period key. Close this up, and I want to square this. Hit enter, and I did it before the calculator did it. All right, what we're doing is we're multiplying this by itself by FOIL. And don't forget that I squared is -1, so 49 times I squared is a -49, combining your constants. Calculator had this done about 10 minutes ago. All right, minus 40 minus 2i, minus 40 minus 40, excuse me, minus 40 minus 42i. The calculator did it for me, Mr. Calculator. Such a good friend. All right, once again, there's only really four values. We are working with I. Square root of -1 is defined as I, defined. I squared is -1. I cubed works out to be -I, and I to the fourth is -1. And it repeats itself. I to the fifth goes back to being I. I to the sixth would be -1. I to the seventh, I to the eighth, I to the ninth, 10th, 11th, 12th. It keeps on repeating itself. It only takes on those four values. All right, here's a case where your calculator is going to help you out, but there's a little trick. All right, what he does is he takes I to the 37th, and he says, well, I want to express this as I to the 36 times I to the first. And the reason being is that you can take I to the 36 and express it as I to the second times the 18th power. 18 times 2 is 36. But I to the second is defined as -1. Well, -1 to the 18th power. And even a power makes this -1 into a positive 1. And then 1 times I just gives me I. Wow. He goes through something similar here. It takes 58, which is a nice even number. He calls that I squared times the 29th power. I squared, by definition, is -1. -1 to an odd power is just that, -1. Let me show you what the calculator will do. It'll do it, but there's a little trick to it. All right, I to the 37th, second function, period key. I'm going to raise it. This little caret here, this last column, I'm going to raise it to the 37th power. All right, and hit enter. Now look what it does here. It gives me this, no, it gives me a plus sign. Sometimes it's a plus, sometimes it's a minus. So there's two parts to this. One part has this letter E in it. You want to ignore the portion that has the letter E in it. I want the other portion to the right of the plus sign. You see it's I? Guess what? The answer was I. Now watch what happens with I to the 58. Second function, I. I'm going to raise it, this caret here. Raise it to the 58th power. Hit enter. Now, here again, I see this convoluted answer, but I get this plus sign. Sometimes it's a minus, though. But whatever, it'll be two parts to it. If it's a plus or a minus, there'll be a part to the left, part to the right. This time, it's the part to the right that has this letter E. I want to ignore all this. What I want to say is my answer is -1. There you see it. There you see it. Now you're saying, well, why is your calculator? It gets confused with the letter I. It knows letter I, but when it starts raising I to powers, it gets a little confused, and it gives me this really small number. E is like base 10. 10 to the -13th is some crazy tiny little decimal. So it's giving me -1 plus this tiny little decimal. All right, we know the answer is simply -1, like just like we knew up here. The answer was I. I just counted this portion that had this letter E in it, and I wanted the other part. That was all by itself. Sometimes it's to the right. In this case here, this one was to the left, the part that I want. I wanted to ignore everything after the plus sign. Okay, let me clear this off. Conjugates. We kind of ran into one of these. I did a problem where you had a binomial in the denominator, and we had to multiply by the conjugate. Here's what he's saying: complex conjugates. The conjugate of -3 plus 7i is -3 minus 7i. Now, I know if I were to multiply these two, my middle term would cancel out because they're exactly the same terms. They just differ by signs. If I multiplied -3 times a -7i, I get -27i. And if I went um, Yeah, outside terms, if I multiplied, or minus times a minus, excuse me, would be a positive 21i. And then this middle term here would give me a minus 21i. The middle terms would cancel out, which is kind of nice. The conjugate of 14 minus 5i is 14 plus 5i. The conjugate of 8i is simply minus 8i. The product of a complex number and its conjugate, guess what, always gives me a real number. In fact, it's going to give me an integer, which is pretty neat. He says multiply these two out. But hey, let's just do this. All right, and then I'll show you what the calculator, what the pencil paper work looks like. So this is 5 plus 7i. Second function, the period key, close parenthesis, open parenthesis, 5 minus 7i. Second function, the period key, hit enter, 74. And let's just see how this plays out. He's squaring the first term, 5 times 5, 25, 5 squared. Positive times negative is going to be a negative. 7 times 7 is 49. I times itself is I squared. But we know I squared by definition is negative 1. 25 and 49, 74. Calculator gave it to me a while back. 8i times 8 second, I don't need the parenthesis here, times a negative 8i, negative 8. Second function, period key. And I get 64. 8 times 8, I'm sorry, 8 times a negative 8, a negative 64. I times I squared. But I squared is negative 1. Negative 64 times a negative 1 is a positive 64. But you see it right there. All right, he wants me to divide here. To negate this imaginary pi, you can't leave radicals, nor can you leave, well, I is actually the square of negative 1. It's a radical. The rule is you can't leave radicals in the denominator. You can't leave the letter I. So to negate that, what we're going to do is to take this guy and multiply it by its conjugate. Now, if I'm multiplying the denominator by 1 plus 6i, the conjugate of minus 6i, I got to multiply the numerator by the same thing, which entails a little bit of work here because I've got to FOIL this out and FOIL this out. All right, and you end up when the smoke clears with something like that, and then what he does, he separates these two under that same denominator. Now you may see the answer written this way, or most times you'll see it written that way. So how can I use my calculator to help me? Well, my calculator won't give me this answer because what it's going to do is take both these fractions and turn them into decimals. But let me just do this. Let me actually do the problem out and see what the calculator gives me. So in parentheses, I've got 2 minus 5i divided by, in parentheses, 1 minus 6i. Hit enter. All right, let me go back to 2 decimal places. I don't want to go have 0. I want to have 2 places here. And hit enter again. All right, so this is what it's giving me. All right. Now, if I had 4 answers and my calculator gave me this, I would say to myself, which one of these answers does the fraction out front equal that? In other words, what is 32 divided by 37? Lo and behold, it's 0.86. What is 7 divided by 37? So you could actually play a little game here. All right, it's 0.19, then you see the 0.19. You can look at the 4, have your calculator do it, and then find out which one of your answers, the fractions equals the decimals that you see in the calculator. And if not, well, then you have no option but to multiply, numerator and denominator by the conjugate of the numerator of the denominator and FOIL it all out. Do all the algebra. Or let your calculator do it and then kind of play, which one matches my correct decimal. I'm trying to make sure that this here is that decimal and this fraction is that decimal. All right. That's pretty much that.